Okay, so this is the outline of chapter 31. So we will introduce LC oscillations, and then we will talk about the damped oscillation in an RLC circuit, and the force oscillation of the free simple circuit, and then talk about the series RLC circuit. Okay, so yeah, when you study this chapter, so you may be confused. What is the difference between this part and this part? Okay, so for this one, it is about the RLC circuit without any input. We only have some energy stored in the L or C, and then after that moment, the energy will be oscillate between the LC circuit. And here we talk about an RC circuit with the AC source, with a sinusoidal source， 有一个正弦的一个电源 ，OK， 那它就会震荡 ，OK。So and the final part will be the power in AC circuit, and also we also talk about the transformers. Okay, so here is electromagnetic oscillation. So yeah, so we have actually the electromagnetic oscillation is about the LC circuit. Okay, it's about the LC circuit. So yeah, so let's start at this point. Okay, the figure A. Okay, so here we have L and C in series, and then without connecting any sources, any other L's. So we only have L and C connected in series or in parallel. It doesn't really matter because it is just a single loop. Okay, so you can consider this is series, this is series, or this is parallel. So yeah, only LC together. It doesn't really matter whether it's series or parallel. Okay, but anyway, we have an LC circuit. So at the beginning, we assume all the energy are stored at the capacitor. Actually, you can arbitrarily stop at any subfigure. At any subfigure. Okay, it's okay, but yeah, we can just start it here. Okay, so all the energy are stored at the capacitor, and then no energy stored at the inductor. Okay, so in such a way, we have a UE is maximum, and then UB is zero. UB is zero. And then I'm not sure whether you still remember what is the expression of UE and UB. Okay, if you don't remember, so actually UE is 1/2 CV square, and UB is 1/2 LI square. And I hope you can remember it. Okay, so it means that if UE is maximized, which means this VC is maximized. VC is maximized, and I is equal to 0. I is equal to 0. Okay, so some moment later, or maybe at t equals to 0 plus, the charge will start to discharge. Okay, so in such a way there will be current going counterclockwise, so to discharge this capacitor. And as much as there is charge going counterclockwise, which means that there will be some current going clockwise, and in such a way, this current going through this inductor, it will be energy stored in this inductor. So it's somehow like some energy stored at the capacitor going to the inductor, and some moment later, the UE, the energy stored at the capacitor, decrease, and then the UB started increase until a certain moment, UB and UE will be equal to each other. Okay, so which means that the sum of the energy stored, or maybe half of the energy stored at the capacitor, or half of the energy stored at the inductor. Okay, and at this moment, yeah, this charge is smaller. This charge is small, not actually half of it. Yeah, you can consider if UE is at this moment, if UE prime is half of UE, then this VC should be should be the VC over square root of 2, over square root of 2, then this power will become half, okay? So yeah, so at this moment, okay, this VC prime equals VC over square root of 2, yeah, something like this. And then this energy will go to here, okay, actually store at the magnetic field or the B field induced by this inductor. Okay, and sometimes later, okay, all the charge of the capacitor discharges, and then so in this case, we don't have any potential difference across this capacitor, and then all the energy are stored at this one. Okay, so UB is maximized, UE equals 0. And then sometimes later, okay, so this current is maximized, but it will start to decrease, but still this current is going counterclockwise, okay, but becomes smaller in magnitude. So in such a way, we have positive charge at the bottom plate, and then negative charge at the top plate, okay, for the capacitor. But actually, since this is a square, so even negative VC is a positive value. So some moment later, we will have a half of UB, half of UE, okay, for the total power of the total power. So yeah, so this one and this one is similar, but the difference is that here we have a positive negative, here we have a negative positive, and the other L's are the same. Okay, and sometimes later, okay, this charge become maximized, and then the current here will become smaller and smaller until 0. Okay, so this is opposite to that part. Okay, so I equals 0, okay, but here positive on the top plate and then negative on the top plate. Okay, so this is reverse case. And then sometimes later, this charge will be going this way again. This charge will going this way again, going clockwise again, and then going back to this, and then this. Yeah, somehow similar to that one. I don't try to go through it one by one, but yeah, after going back to here, okay, you will start another oscillation. So it's like oscillation. So it doesn't really matter which part, which subfigure you start. Yeah, you will loop forever. And actually, we don't have resistor, so which means that all the energy, no energy will be lost. Okay, no energy will be consumed by any device. So here, as much as we have a conservation of energy, so yeah, no energy. We have no energy loss here, and this oscillation will maintain forever. Okay, so this is UE equals Q square over 2C, or you can write it as 1/2 CV square. It just depends which form you like. You can just make use of Q equals CV, so that you can also have 1/2 CV square, and then UB L 1/2 LI square. Okay, so here we try to compare this LC oscillator with the Brock spring system, okay? But yeah, I usually learn it as a spring mass system, okay? So they should be referring to the same thing, okay? Spring mass system and Brock spring system, okay? So this mass is actually the Brock, okay? Spring. Okay, so yeah, so this actually means if we have a spring and then connecting to a mass, okay, then if you try to drag it a bit and then you release, and then it will start to oscillate. And then if we assume this spring, okay, does not have any energy loss, and then this oscillation will also run forever. Okay, so here is the comparison is that we consider in the energy point of view. Okay, so for the LC oscillator, we have this, okay, 1/2, okay, 1 over c q square or 1/2 cv square. And here we have a block, which is 1/2 mv square is the kinetic energy. Okay, so for the inductor, we have a 1/2 Li square. So we can somehow relate this K to be this 1 over C, this X to be this Q, and then this M to be this L, this V. This is the velocity, is the current, okay, not voltage. And actually this V is the first derivative of the displacement. And also this I is the first derivative of the Q, okay? So here we have the first derivative. Okay, from this variable to this variable, we have the ddt. Okay, from this one to this one, we have a ddt. So this is the analogy, 就是那个类比. Okay, so it means that if we derive any ODE for the spring mass system, you can actually change the variable from Q to X, 1 over C to K, and then I to V, L to M, and then you can get the solution for the other system. Okay. And actually here we have this thing. This thing is the natural frequency or the oscillation frequency. Somehow we can call it the natural frequency. But actually this is the angular frequency. Omega is the angular frequency. If you would like to make it a linear frequency, F should be like 1 over 2 pi square root of LC. Okay, so this is the angular frequency of the oscillation, or sometimes we call it the natural frequency. Okay, so which means that if we try to replace L by M and then 1 over C by K, then we can get the frequency for the spring mass system is actually K over a square root of K over M. Square root of K over M. L to be M. Okay, so M here. C to be 1 over K. So K go to the top. Okay, so this is the natural frequency for this one. Okay, so here we try to tell you that why it will oscillate. Okay, using some mathematics. Okay, so first of all, we have the energy method. So in the chapter 27, we also introduced the energy method for solving the resistive circuit. But at that time, it's somehow like making things complicated. But here, although I should say that when I learned the circuit theory in my bachelor study, I did not read this energy method. Yes. So, but when I teach this, I feel that this method is quite interesting. This is quite interesting. So, I think we can take a look at it. So here it says we can consider the total energy of the LC oscillator. So total energy U presents at any instant, any time in an oscillating LC circuit is given by this. Okay, U equals UV and UE because we only have a capacitor. The capacitor and the inductor. Okay, so we only have energy stored in these two devices. Or only these two devices can store energy. So UB is 1/2 Li square and UE is 1/2 CV square or Q square over 2C. Okay, so nothing special here. Okay, so and next we try to consider the conservation of energy. So which means that the energy will not change for this system. The total energy stored in this system will not change. That's what we call conservation. 能量守恒嘛，就是能量就不会增加也不会减少。OK， 它只会转移，就是VB 变成UE，UE 变成UB， 但是它不会总量不会增多减少。 So we have this du dt equals 0. Okay, so we try to take the derivative of this expression and then make it equal to 0. Okay, so try to take the derivative of this. Okay, so here we have L is a constant, so L putting in the front, and then I square, taking the derivative will become 2I. So these two cancel with these two, so we only have I. And then we also have the chain rule, so we also need to take the derivative of this I. So we have a di dt here. So this is due to the chain rule. Okay. And then next, we take the derivative of the second term. So 1 over, or maybe 1 over c. 1 over c is the constant, so we put it here. And then 2q. Okay, the derivative of 2q is, q squared is 2q. So these two cancel with these two. So we only have a q here, and then also for the chain rule, we need to take the derivative of dq dt. These two terms are due to the chain rule. Okay, so this is du dt equals 0. Okay, so in such a way we can have, let's see. So here we need to do some substitution. So of course we have I equals dq dt. So which means that this I and dq dt are the same. Okay, and we assume that it is not always equal to 0. So we can actually cancel this term. Okay, di and dq dt are the same. And then we also try to take the derivative on both sides. So we have di dt equals the second derivative of q. Okay, so we try to substitute di dt by this second derivative. So this is second derivative. So it becomes d2q dt2, and then in front we have an L, and then plus q, or maybe I can write it as 1 over c times q. Okay, because q is the unknown function. So finally, we can just divide both sides by L. So we have this second derivative of q plus 1 over LC. Okay, 1 over LC times q equals 0. Okay, so this is actually a second order constant coefficient ordinary differential equation. Okay, so we have this. And actually, we can use another method called the potential method, or actually, we use the KVL. We actually use a KVL. So, yeah. So I try to derive it like this. Okay, we have an L and C. This is L. This is C. And let me assume this is VC. Okay, this is VL. Okay, so plus minus. Okay, so in such a way we have a VL plus VC equals 0. Okay, so we start from this point. Okay, going down becomes 0. Okay, so VL plus VC equals 0. And then we also assume the current I in this direction. So this I follows this direction. So we have a VL equals L di dt, and then I equals C dv dt. Okay, so here we have a VL equals L di dt, and also I equals C dv dt. Okay. Okay, so here we can just plug in I to here. Okay, so here we have LC and then the second derivative of VC like this. Okay, yeah, because C is a constant, we can just put it out, and then this is the first derivative and then another derivative. So we have altogether the second derivative, and then we can just plug in this VL to there. So we have a LC d2 VC dt2 plus VC equals 0. Okay, and then we can just divide LC on both sides. So we have a D2 VC dt2 plus 1 over LC times VC equals 0. Okay, so this is also a second order constant coefficient ODE, but yeah, there are some difference. Here we have VC here, but here we have Q, but the other part are the same. Okay, so this is the interesting part for the linear system. Actually, if you take out any variable in this circuit, okay, you can also write it as d2i dt2 plus 1 over LC times I equals 0. Or maybe you can also write d2 VL dt2 plus 1 over LC VL to be 0. Okay, so this is due to the this is a linear system. Okay, so no matter how you change the variable, then they're the same. But what is the relationship between Q and VC? Okay, actually Q is Q. If you take the derivative of Q, okay, it becomes a current. Okay, so it goes to here. Okay, if you don't believe, you can try to do some change of variable, like you try to take the derivative of this thing, and then you multiply C on both sides. Then this CdV CdT will become I, so it becomes d2i dt2 and then plus 1 over LCI equals 0. And then if you try to take the derivative of this thing, okay, this, or maybe you can just put I to be dq dt here. Okay, so it becomes third derivative and first derivative. Okay, and then you can actually cancel the one order, so that it becomes an ODE for the charge. Okay, so yeah, so that's the interesting part for the linear system. So actually we can actually derive the equation for this LC circuit, okay, which is a second order ODE. And then actually I still don't solve it yet. Okay, to really solve it, it is not that difficult. So we try to change this second derivative. We change it to s squared, and then plus 1 over LC, and then this is an original function. We make it a 1. Okay, so s LC and then times 1 equals 0. Okay, so this is interesting. This is a positive value. So s squared becomes negative 1 over LC. So s becomes plus or minus j over square root of LC. Or I. Okay, so here j is a square root of negative 1. Okay, so if you still remember, if we have complex conjugate roots, the solution will be like VC equals, let's say this is a capital VC, this is a constant, and then times, or maybe I should write it as something like A cosine of T over square root of LC plus B times sine of T square root of LC, something like this. Okay, the general expression will be like this. But usually for the textbook, it will only write out it is a cosine or it is a sine. Okay, with a phase. Why it will be like that? Actually, in the high school trigonometry, you know, if we have A times cosine with a frequency plus B times sine of a same frequency, you can make it like this is a VC times cosine T over square root of LC plus an angle. Okay, you can try to make it like this A is equal to something like cosine of phi. Okay, and then B equals negative sine of phi, okay, something like this. Okay, so and then we can try to find out what phi is, and then we can make it a single cosine, okay, with a phase here, and this is the amplitude. So in the textbook, it will write it as something like this, or sometimes it just ignore this phi, okay, it just ignore this phi. You say, oh, I just take the initial point is a 0, so yeah, to remove this phi. Yeah, but anyway, if you just put it there, it's just a phase, okay, it's a phase， 就是一个相位，就是这个是正负，这个是相位。Okay, so just as what I mentioned, VC have an expression like this for this ODE, and then Q also have a similar expression for this ODE. So this is nothing but a cosine. Q, capital Q is a constant, is the maximum Q, and then times cosine omega t. Okay, here omega is 1 over square root of LC. Okay, so this is actually omega equals 1 over square root of LC. Okay, for the spring mass system, we can also derive the similar ODE. So suppose this is a mass, this is a spring with a coefficient K. Okay, so actually here we have a force. We have a force acting on this mass equals to negative kx. Okay, according to the Hooke's law. Okay, so here we have F equals negative kx equals ma. Okay, equals ma. Okay, so this is actually the second Newton's second law of motion. Okay, but we don't try to make it like ma. Ma is too stupid. Okay, we don't do too much. So we try to make it like the acceleration is the second derivative of the displacement. So this is actually m times d2x dt2. Okay, the second derivative of the displacement is the acceleration. So yeah, making it like this, we can do more things. Okay, so here we have a m d2x dt2 plus kx equals 0. Okay, so in such a way we try to divide m on both sides, so we have a d2x dt2 plus k over mx equals 0. Okay, so this is a second order ODE. Okay, so this is s squared plus k over m times 1 equals 0. So here we have s equals plus or minus j over, or maybe like j times square root of k over m. Okay, so this is the omega. This is the omega. Omega equals square root of k over m. Okay, this stuff. Okay, so this is a conjugate root. So we have x equals, let's say capital X cosine of omega t plus phi. Okay, similar procedure. Okay, so that's why I'll say yeah, this is a linear system. Okay, so a linear system, yeah, share similar properties, although one is an electric circuit, one is a mechanical system. But actually, in behind that, the mathematics are the same. Actually, the same. Okay, so here we have this Q for the second order ODE with respect to Q. And actually, we can just plug in this one to here. We can actually have a dq dt to be the I. So the derivative dq dt, so we have Q, and then the derivative of cosine is negative sine. So here we have a negative Q sine of omega t plus phi. And then we also have the chain rule. Okay, take the derivative with respect to t. Okay, so we have the omega. So this omega is due to the chain rule. Okay. So we have a negative omega q sine omega t plus phi. And if you want to further know what is VL, VL will be L di dt, and then you can plug in this one to here, and then you take the derivative, and then you will also find VL. What is VL? And then for the VC is nothing but Q over C. Q over C. Okay, so yeah, so here actually we get the expression of Q. We also get the expression of I, so that we can actually plug it back to here. We have UE equals to Q squared over 2C. So after plugging the Q to here, we have capital Q squared over 2C, and then cosine square of omega t plus phi. Okay, so this is the energy stored in the E field. And for the energy stored in the B field, okay, we have UB equal actually the same thing. It's actually the same thing. Okay, so you can try to take the square. Actually, UB here is 1/2 Li square, which is 1/2 L, and then I square will be omega square Q square, and then sine square omega t plus phi. Okay, the square of negative sign become positive. Okay, like this. Okay, here it says it's Q square over 2C. We have 2Q square here, but whether it's 1 over C? Okay, the answer is yes, because we have omega equals 1 over LC. Okay, so which means that omega square equals 1 over LC. So which means L omega square is actually 1 over C. So this thing is actually 1/2 Q square over C, and then sine square of this thing. Okay, we have a Q square over 2C. So here we have a Q square over 2C sine square of this same thing. Okay, so after getting the expression of UE and UB, okay, we can actually observe that, okay, actually it just try to take a phi equals to 0 on this graph, and then it will say the maximum value for UE and UV are both Q square over 2C, because the maximum value is cosine to be plus or negative 1, okay, plus or negative 1 square will be 1, okay, so the maximum value will be Q square over 2C for both cases. And if you add them together, UE plus UB, okay, this is the common factor, and then the remaining stuff is cosine something plus sine square of something, cosine square of something plus sine square of something. So in high school trigonometry, you know that this thing is actually 1, okay, so we can quickly find that UE plus UE plus UB is actually Q square over 2C. It's a constant. Okay, so it actually matches what we assume is the conservation of energy. So this is the conserved energy. Okay, so when E is maximum, BUB is 0, and conversely. So it's just mention something related to this graph. Okay, so at the beginning, it just tell you we have some observation, but actually it's like he already know the solution, and then try to explain it visually, telling it, oh, we observed this thing, but actually this observation should be actually comes from this kind of solution. Yeah, you have no way to look at the voltage, look at the current. Yeah, but actually the mathematics tells you, okay, the phenomenon of the LC circuit is like this. Okay. OK， 所以这个就是 LC 电路的话，就是它是一个简单来说，它是一个2次的微分方程。那2次微分方程它是特征值是序数啊，正负 J 除以开根号 LC 啊，所以它的解就是一个 cosine。那这个 cosine 啊，原则上它应该是 A cosine 加 B cosine， 加 B sin，OK， 同一个频率的。那但是你三角函数学过的话，就是说你可以把 B cosine 加A cosine 加 B sin 写成一个 cosine， 但是有一个相位存在。OK， 所以这里就是有一个 cosine omega t 加 phi 有一个相位在。那前面就会有一个正负 ，OK， 然后这边就是说，我们解完那个 Q 出来了，然后我们也求出来那个 I 带进去之后，我们可以发现 U1 是长这样 ，UB 是长那样，加起来它就是一个常数 Q square 除以 2C， 就是那样。OK， 所以相对来说 ，LC 震荡是比较简单的，后面的话会比较复杂一点。Okay, so here we have a sample problem. Okay, so it says a 1.5 microfarad capacitor is charged to 57 volt. A charging battery is then disconnected, and a 12 millihenry coil is connected in series with the capacitor so that LC oscillation occurs. OK， 所以他就告诉你说，我怎么充电在这个电容，然后这个电容就接到 LC， 所以这个 LC 就会有一个起始的一些能量储存在那边。So what is the potential difference VL across the inductor as a function of time? Okay, so just as what we have a D2Q dt2 plus 1 over LCQ equals 0. Okay, so this is still the LC oscillation. And then it will still give you Q equals capital Q cosine of omega t. Of course, we will have plus phi, but it just tells you that at the beginning it will be maximized. Which means that Q0 will be maximized. Okay, so here we have a Q equals CV. Because at the beginning we have a capacitor connecting to this battery of this EMF 57 volt. So this is nothing but 1.5 times 10 to negative 6, okay, times 57. Okay, so it is 8.55 times 10 to negative 5th power C. Okay, so this is the charge, the initial charge at the capacitor. Okay, so here we have a VL equals L di dt. And this I is actually the derivative of Q. So we have a second derivative of Q with respect to time. Okay. And in such a way, we can just plug in this expression to here. So here we have a L d2 dt2, and then we have Q cosine of omega t. Okay, so here we have a L times Q. Okay, Q is a constant, so we can just move it to the front. And then we need to take the derivative of the cosine. Okay, it becomes negative sine, and then take the derivative again, become negative cosine. So here we have a negative cosine of omega t. And then we need the chain rule. Okay, the chain rule, taking derivative of this thing becomes omega, but we need to take the derivative of 2 times. So we need to multiply by omega squared. Okay, so altogether we have a negative LQ omega squared cosine of omega t. Okay, and then here we try to plug in omega equals 1 over square root of LC, okay, or omega square equals 1 over LC. So it will be negative LQ and then times 1 over LC cosine of omega t. So L and L cancels. And then finally we have a negative QC over cosine of omega t. Or actually this is nothing but the V, okay? Negative V cosine of omega t. And this V is, of course, this 57. So this is negative 57 cosine, okay? We can actually find omega, okay, which is 1 over square root of LC. So here we have a 1 over T over square root of L. L is 12 millihenry. 12 times 10 to the negative third times C. C is 1.5 times 10 to the negative 6. Okay, so this is a negative 57 cosine 7,500 7,500 T. Okay. Okay, and then the SI unit is V. Okay, like this. And actually, this thing should have a SI unit of a radian per second. This is radian per second, and then multiply by the second. This is actually a radian. This is a radian. Cosine, you can take a radian. Okay. So this is the voltage. This is the potential difference across the inductor. And then for part B, what is the maximum rate dIdt max at which the current I changes in the circuit? Okay, so yeah, so actually we have I equals negative omega q sine of omega t. Okay, so this is actually come from here, negative omega q sine omega t. Okay, so we just ignore this phi. So we have a negative omega q. We have a negative omega q sine of omega t. Okay, so actually we have derived that before. So yeah, so we can just take the derivative didt to be negative omega q. The derivative of sine become cosine of omega t, and then the chain rule, we have omega, so we have omega square here. Okay, so yeah, so it asks you what is the maximum rate. So this is a constant. So in order to make it the maximum, we can try to make this cosine of omega t to be -1. Okay, -1, because we have a negative sign in the front. Okay, so making it this cosine to be -1. Okay, so this whole thing of dIdt max will become omega square q. Okay, become maximized. This is when cosine of omega t equals -1. Okay, can take this value. Okay, so actually this is nothing but q over LC. Q over LC, or Q over C is actually the V. So we have a V over L. V over L. So V is 57, and then L is 12 millihenry. 12 times 10 to the -3rd. So this is 4,800. 4,800. Okay, and what is the SI unit? Okay, so we have a dIdt. Okay, so this is current, this is time. So the SI unit should be A over S. Okay, A over S. OK， 有没有问题？Okay, so here we have a so-called damped oscillation. Okay, 那个中文叫什么？中文叫做阻尼啊，阻尼。为什么这个中文我现在不知道为什么，反正它是叫做 damped oscillation 啊 ，damped oscillation。它有所谓的 over damp、under damp， 还有什么 critical damp。反正也无所谓啦，反正就是它是不是在震荡的意思，这是叫做 damped oscillation。那就是一个 RLC circuit， 它如果有一些 initial energy 在的话，它就会所谓的 damped oscillation。Okay, so if you just look at the solution is like this. Okay, you still have this Q, you still have this cosine, okay, omega prime t plus phi. Okay, this omega prime is not 1 over square of LC. Okay, it is a little bit different. Okay, the difference is that omega prime is square root of this big thing. Okay, so we still have omega square here minus something. Okay, so first of all, if you just ignore this part, okay, so omega prime becomes square root of omega square, which is at omega. Okay, so this is the original 1 over square root of LC. But here we try to subtract something. Okay, usually this part should be small. Okay, so this whole thing is a bit smaller than omega square. So taking the square root, the whole thing is also slightly smaller than omega. Okay, so yeah, so this is this part, and actually in the front we have this thing, exponential to negative R over 2LT. Okay, R over 2LT. Okay, so we have this exponential. So if your mathematics is good, so you can have some feeling about that. So this is actually due to the second order ODE, and then yeah, with this stuff, and then finally the solution S is something like alpha plus J beta. Okay, so this negative R over 2L is this alpha, and then this omega prime is this beta. Okay, so that's why we will have this solution with this phi. Okay, so here we can go back a bit. So yeah, so here for the damped oscillation in the RLC circuit, actually we have R here. Okay, so we have RLC in a loop. Okay, so in such a way, of course the LC will oscillate, but this R will consume energy because the power consumed by this R resistor is P equals I square R. So as much as there are charge and discharge operation, there will be current. Okay, so this current will make the energy consumed by this resistor become some heat. Okay, so the yeah, the total energy will become smaller and smaller. Yeah, because this energy consumption is a positive value. Okay, so here we try to also consider this RLC circuit from the power point of view or the energy point of view. Okay, so the total EM energy U is still UE equals UB plus UE. Okay, so up to this part is the same, but we don't have du dt equals 0 anymore. Okay, for the pure-phase LC oscillator, we don't have resistor, so we don't have any device to consume energy. But here we have LC series with this R, so in such a way we have du dt equals negative I square R. Okay, so this is the U is the total energy. U is the total energy, and then taking the du dt will become the change of the total energy. Okay, so change of energy is negative to this thing. Okay, so this is the power. This is the power generated or consumed by the resistor. Okay, so here we should have a negative sign. Okay, to represent this is power loss. Okay, this is for the power loss. So the total energy decrease as energy is transferred to the thermal energy due to the resistor. Okay, so the rate of the transfer is du dt equals negative I square R. Okay, so we have this power dissipation. Okay, so similarly, we can also take the derivative of this, but it is not equal to 0 anymore. It is equal to negative I square R. So in such a way, we have, taking the derivative, we still have Li and then di dt. Okay, so du dt equals this Li di dt plus Q over C dq dt. Okay, if you remember, we just did it just now. Okay, so this stuff is equal to negative I square R. Okay, so you should remember that I equals dq dt. Okay, so we can do some cancellation. We can cancel this one with this dq dt with this I. Okay, I dq dt are the same thing. So we cancel this I dq dt and then one of the I here. And this is L di dt. And then QC. Okay, so also di dt should be the second derivative. So it becomes L d2q dt2 and then plus Q over C and then equals negative dq dt. Okay, so this is the second derivative, the first derivative, and the original function. Okay, so here we try to divide L on both sides. So here we have a second derivative of Q going here, and then we have we still have this. We still have this R here. So here we have R over L, and then dq dt. And then finally, we have a Q here, and then 1 over LC. So this is also a second order constant coefficient of the. Okay, but when we consider this resistor here, we have this additional term. This additional term refer to the energy loss. Okay, if you just cover this energy loss, it is actually the second order ODE for the LC oscillator. Okay, so to solve this second order ODE, okay, so we try to change the second derivative, becomes S squared. Becomes S squared plus R over L times S plus 1 over LC times 1. Okay, I don't try to write it again. Okay, so it becomes S squared plus R over L times S plus 1 over LC. So it's a second order algebraic equation regarding to S, okay? So of course we have 3 different cases when b squared minus 4ac is larger than 0, equal to 0, and or smaller than 0. But we just simply ignore the first 2 cases. Ignore the delta. We just ignore delta equals delta bigger, larger or equal to 0. We just ignore. Okay, because these 2 won't give you any oscillation. Okay, this is not what we concern. So what we only concern is delta is less than 0. Okay, for delta is less than 0, we will have this. We will have this solution. Okay, so if b squared minus 4ac is less than 0, this second order algebraic equation will have complex conjugate roots. Okay, so for the complex conjugate root, it will give you something like this is the real part, this is the real part, and then the imaginary part will be like this. Okay. Because it is just like the S will be 2, okay, and then negative B, negative R over L, and then plus or minus. We have B squared R over L quantity square minus 4AC, 4 over LC, 4 over LC. So this is the S, okay, and of course this stuff is less than 0. So it becomes negative R over 2L and then plus or minus J, and then we just swap it 4 over LC minus R square over L square. Okay, so this negative R over 2L is actually this thing. And this square root is this stuff. Is this stuff. Sorry, it should be like this. Okay, something like this. Okay, because if this 2 is putting inside, okay, these 2 and this 4 cancel. So we only have 1 over LC here minus this R square over 4L square. Okay, so actually this is actually this omega square, and this is omega. Okay, so yeah, according to this characteristic equation, we can get the solution. Get the solution to be like this: Q, capital Q times exponential to this part. This is the real part of this characteristic value, and then this is the imaginary part of the characteristic value. Okay, like this. Maybe I should solve it here. Okay, so